Hey, so today we're talking about rational exponents. And so I want to make sure that we do a few examples and learn about how rational exponents work. It's a great idea to write some of this stuff down in your notes because even though I'm taking the video of it, you'd have to watch the video again in order to glean the ideas again. It might be better to just have your own little version written down in your notes. And you may have noticed when you were doing IXL things over the last couple days, it could have been really helpful if you had some little examples in your notes of how things operate that you could just glance at. So it's really good to have this in your notes. So the definition of a rational exponent, which just means a fraction exponent, is that the numerator of your fraction, and I'm realizing now, I used the letters that look the most like each other that I possibly could.
Yeah, I'm not going to be able to.
B and P and Q. I didn't use D because they're all the same. They're just like rotated and reflected different ways. I'm very sorry about that. Let's color code this a little bit. So we'll say P for power, okay, up in the top there, P for power. And the top, the numerator of your fractional exponent is just a power, right? Imagine that you had 3 to the 1, right? That's also 3 to the 1 over 1, right? 1 over 1 is the same thing as a power of 1. So notice we're saying when you write it as a fraction, this top number is a power. We're saying 3 to the 1 when we do that. If we change this to, let me erase that real quick, and just change it to 3 to the 3, notice that's also 3 to the 3 over 1 as a fraction, and this 3 is still a power, right? The numerator number is just a power, just a normal power, because it's just like if you had that over 1, right? But the bottom number is a Q. We'll make it a blue Q, because those rhyme nicely. Blue Q. We'll put a tail on it too, so it's a little bit tail. All right? Blue Q with a tail. That's going to be the root, like square root, cube root, fourth root, fifth root, sixth root, right? Whatever the denominator is, you're going to do that type of root. So if Q is 4, you're going to do a fourth root. That's what that means. And the way that I like to try and remember this, it's a little silly, but I like to remember this. I wonder if I can get brown. Brown an option?
I'll think of a maroonish.
More. Let's get brown. Here we go. Brown. All right. So the way I like to remember this is it's kind of like a tree where the roots are down at the bottom. See what I did? Root down at the bottom. And then we can go green. We got like the power of the tree, these big muscly, bushy leaves. The power is up at the top. The roots are down at the bottom. So that's just a little memory device, right? So you can picture your fraction. You got the power at the top, root at the bottom. So when you look at my example over here, on this side of the board, we've got 3 to the fraction. All that means is to the 5th power, but the 4th root. And it doesn't matter which order you do those two ideas in. So you could do 3 to the 5th on the inside here, with the 5th power, and then take the 4th root of the answer. Or you could do the 4th root on the inside, like I have down on the bottom, the 4th root, and then take to the 5th power of that. It doesn't matter what order you do the power or the root, because they're both exponents, right? So it doesn't matter what order you do them in. If you think of order of operations, all the exponents happen at the same time. So it doesn't matter what order you do the top or bottom part of the exponent. So if we look at some quick examples of this, and we just try to evaluate some of these things, we want to first ask ourselves, well, what is that 1/4 power actually doing? What's it doing? Go for it, Amanda. The 4th root of 16. So we have to ask ourselves, something to the 4th power is going to be 16? Do you happen to know what that is? 2. 2 to the 4th is 16, so the 4th root of 16 is 2. Gotta be careful with my words there. Is that good? Now, if we bring negativity to our exponents, we can say this is 1 over the 4th root of 16. Nice. Notice my fraction is not a negative fraction, right? That was not how negative exponents work. Negative exponents make 1 over what we would have as a positive exponent. So Renee says that's obviously going to be 1/2 when we boil that down. All right, evens up. Now, come on, scroll bar. Woo! All right, even. 8 to the 2/3. What's going on with that?
It's going to be 8 squared the under cube root.
We could do 8 squared and then take the cube root, or
You could
we could do the cube root of 8 squared. Now, which one of these is going to work out a little bit easier for us? Cube root of 8 and then square it. So let's look at this guy, because the cube root of 8 is 2, and then we'll just have 2 squared is 4. Otherwise, we would have had 64 under there, and we would have had to figure out what the cube root of 64 is, which, I mean, now we know it's going to be 4, right? Because it's got to be the same answer, but that might not be a cube root that you know. All right, what if we had the negative version, 1 over cube root of 8 squared. We know the bottom now is 4, so this is 1/4. Boom. Now, right around this moment, there's always somebody that asks me the question, well, but how would you put that in the calculator? And I always say, well, could you just put this in the calculator? You could, right? You could just make your exponent a fraction when you put it in. So 8 to the negative 2/3, a little fraction up there in the exponent, and it'll pop out the answer. But then they always say to me, well, that's not what I mean. What I mean is, if I didn't know the cube root of 8, how could I put that in the calculator? And some people say, oh, well, you can type in a special little code to get cube root. I think Rochelle had it for us. It was CBRT or something to get cube root. But I always say, well, to me, it would be a lot simpler to just type in 8 to the 1/3 power, because that's cube root, right? And that'll work for any kind of root. So let's say you have the 7th root of 512, and you have no idea what it is, right? Because that's not one that's just in your brain. You say, well, hey, I can toss this in the calculator, 512 to the 1/7 power, right? And that way you can use your calculator to do any type of root you want much more quickly. So this is a great way to convert things so that you can always just toss it in the calculator and figure out your square roots, cube roots, any kind of root. All right, next level. What if we try to put our rules about how exponents operate together with our fractional exponents? So what's going to happen in here with our 2 exponent outside the parentheses? Good, it's going to apply. Thank you for using the word apply. It's going to apply to both of these, and the rule is it's going to multiply together. So we're going to have a to the 1/2 to the squared is just a to the 1. We'll also have b to the 1. I think we're done. Now, I guess I have this feeling every time I put a box around an answer. I say, hold up, Mr. Hunter. Should I have thought super deeply about this before putting that box around? The answer is usually yes, right? So what might we think about before we haphazardly, oh, I got to erase my box, before I haphazardly put a box around my answer? What could we possibly be losing as information in our simplified situation here?
what A or B cannot be.
What A or B cannot be. If this represents a square root of A, what kind of number can't A be? If I'm taking the square root. You take the square root of 0.
Oh, 1.
Negative.
You take the square root of 1.
Negative.
You can't take the square root of negative, right? You get an imaginary result. Now notice, if A was negative here, would we get an imaginary result?
No.
No. But if A was negative at the beginning, we'd get an imaginary result. So has information changed? It has. So we would have to restrict this to A and B cannot, I guess I want to say they can't be negative. How could I write they can't be negative in the easiest possible way?
Be greater than 0.
A is greater than or equal to 0. B is greater than or equal to 0. Well done. So that way, I can say there's a restriction here to keep my values real, right? That A has to be greater than or equal to 0. B has to be greater than 0. To keep my values real at the beginning, which means I'd have to keep that real, keeping it real for the ending as well. All right. Sorry about me. All right. Part B. Please, no atrocities. What do we do with that 2? Well, we're certainly not going to distribute it.
You gotta
I'm glad that nobody went that direction. We got to expand it. I like that word, expand. So, is that what you were thinking too, Renee?
They apply it?
You can't apply it because of the plus. The plus is stopping us. It's only when the things are multiplied. So, we can expand it though, and FOIL our objects together. We'll have first times first, where we do what with the exponents? Add them. So that's A to the 1. All right. Outside, we can't do anything because they're different bases, so we just got to write that out. A to the 1/2, B to the 1/2. Inside, again, A to the 1/2, B to the 1/2. And last, did that wrong. Last. Go away. Go away. Stop nonsense. You like that, Ethan?
I'm pretty sad.
All right. B to the 1/2 times B to the 1/2 is just B. These combine together, so A plus 2, A to the 1/2, B to the 1/2, plus B. I also might want to rewrite it as A, no, not even, A plus 2 square root of AB plus B. Wait, I threw a box around it. I threw a box around it. What do we have to think of? Did I lose anything? What is that original?
No, you didn't lose anything.
Anybody other than Renee? Did we lose anything? In the original,
They both have to be equal or greater than or equal to 0.
and
don't they?
again, they both have to be greater than or equal to 0, because up here, we're taking square
Doesn't it
roots.
say that though with the root?
But it doesn't on the B that doesn't have a square root here, or the A that doesn't have a square root there.
Well, yeah, but you have an A and B in this group.
Oh, so you're saying, well, but in this one, if both of them were negative, this would come out as a real number anyway. So I think we still do have to tack on A is greater than or equal to 0. B is greater than or equal to 0.
But
It was,
you
it
still
was
have-
close though. I see what you're getting at, Amanda, and this one's closer to it being okay to not have that because of that middle term. But it's not quite.
Why not with the middle term? Like, why not?
Because if A and B were both negative, this would come out real, right?
Yes.
But if only A was negative, or only B was negative, this would come out imaginary.
Mm-hmm.
So it mostly covers the case, if one or the other is. But the original also doesn't work if both of them are negative. Right? The original doesn't work if both A and B are, if they're both negative. And so we have to make sure that our answer also doesn't work if they're both negative. So I mean, technically we can tack on here at the end, A and B are both negative as the extra information that we don't want to lose. A and B can't both be negative.
Oh, my dyslexic brain is doing backflips right now.
Good exercise. All right, last example. So, if we got 1 over 2 to the third, how could you rewrite that? 2 to the negative 3. So what's x? X is negative 3. I lied. This is the last example. Now those are not the same base. One has a 27 and one has a 9. What do we need to do?
Figure it out.
We need to figure it out, that's true. But we need to figure it out by getting the same base. So instead of 9, I would want to write 3 squared to the x plus 1. And instead of 27, I could write 3 to the what?
3 to the 3.
3 to the 3 square rooted. Okay? So I've got 3 to the, what do we do with these exponents?
Multiply.
Multiply 2x plus 2. What do we do with all this stuff?
You can do power over root. Do it.
Power over root. Thank you. So 3 to the
3 over 2.
3 over 2. Got red 3 up there. All right. Then all you would have to do is say those two powers have to be equal. So you set those powers equal to each other and you solve for x. All right, let's see if we can do that. Subtract 2 here. I'd rather subtract 4 halves here, because that's the same, right? And we'll have 2x equals negative 1 half. I'd like to divide by 2 on both sides, but over here it's probably easier to say multiply by 1 half, because that's the same as dividing by 2. And we'll get x is negative 1/4. Which we could then go over here and just check on a calculator that everything works out. Maybe back in the original, we can check the negative 1/4 to make sure that that works. It's always good when you're solving an equation and then plug it back in at the end to check. Because these start to get a little bit complicated. You could always make an error with just a plus or minus, and then you want to make sure you check. Okay?
Can you scroll up?
Oh, scroll way up. Okay, I thought you just moved that one.
Like way up.
Scroll way up.
Yeah, I didn't write this down right.
I got you.
I don't use my.
So, the rest of what you want to do today, hopefully that was quick, I tried not to be too long-winded there, is to jump back onto IXL, and we have the rational exponent IXL things ready to go there for you. Are you all set, Renee?
Yeah, I'm good, thank you.
All right, so it's these topics, and I'll leave this up on the board. I just need to turn the video thing off, and then I'll leave this up on the board for you so you can see them in order. There's a lot. Don't feel like you have to finish in this period. I know you only have like 10 minutes or 12 minutes or something. So you'll have more time to do this. Let's see if I can figure out how to turn the video off